Hi, I'm Kathryne Daniel, and this video serves as an introduction to my most recent publication, which is the first paper in a series of papers addressing constraints on the efficiency of radial migration in disk galaxies. So, radial migration is a process by which transient spiral arms can rearrange the orbital angular momentum of stars and gas in the disk without causing kinematic heating. If radial migration is a very efficient process, then it could have a significant impact on the kinematics, structural, and chemical evolution of disk galaxies. One might appeal to observational evidence of past efficient radial migration in the local disk. However, observational uncertainties make any sort of conclusive signatures of past radial migration difficult to interpret. In-body simulations are another way that people have tried to look at the efficiency of radial migration in spiral galaxies. However, the range and the importance of radial migration to the evolution of the disk in in-body simulations is rather large, going from having little to no impact on the evolution of the disk to possibly giving rise to structures like the thick disk or populating the outer disk with old stellar populations. It might also lead to smoothing of the rotation curve in the disk, as well as even giving rise to the exponential surface density profile of the disk. However, because there's a large range in the parameters and resolution that can be toggled in each one of these in-body simulations, it's difficult to say why the range in the efficiency of radial migration is so broad. So what one might then turn to an analytic understanding of the efficiency of radial migration. Unfortunately, very little has been done in terms of analytics. So our understanding of the physics and the important physical parameters that control and regulate the efficiency of radial migration is poor. So that is the premise of my work. This first paper identifies which stars are in a particular family of orbits that are necessary for radial migration to occur. So radial migration, to give a little bit of background, only happens because stars near the radius of corotation, so in this case, corotation is the radius at which the pattern speed of the perturbing pattern, which is a transient spiral in this case, is equal to the circular orbital frequency of the disk. So near that radius, it is known that horseshoe orbits, which is the name of this particular family, do occur, and that they are characterized by oscillatory orbital angular momentum with little change to no change in the random orbital energy of the star. Analytically, there has been some work to identify which stars, what are the important parameters to determine the stars that are on horseshoe orbits. However, in real galaxies, there are no stars with zero orbital random energy, and the question is, how does random energy affect whether or not a star is captured in a horseshoe orbit? So in this paper, I derive a criterion for whether or not a star is trapped in a horseshoe orbit if it has a given random orbital energy. I derive it in terms of action. Please refer to my paper to see the details of the derivation. And then I assume the epicyclic approximation in order to transpose that into quantities that are more easily understood in terms of the physics of what's happening. So it turns out that the random orbital energy has very little to do with whether or not a star is trapped in a horseshoe orbit. And the important parameter is the orbital angular momentum. And from the capture criterion that I derive, one can define a region near corotation that I call the capture region. The capture criterion predict that the star's mean orbital radius, or in other words, its orbital angular momentum, because the mean orbital radius of a star is directly correlated with its orbital angular momentum. If its mean orbital radius is within the capture region, then it's trapped in a horseshoe orbit. So after that, I numerically tested the capture criterion and to see how robust it is in terms of its power of predictability. And it is, in fact, quite robust. So for any star, if one has the 4D in the disk, the 4D phase space coordinates of a star, and knows the amplitude of the perturbation near corotation, the perturbation being the amplitude of the spiral potential, then one can derive whether or not that star is trapped in a horseshoe orbit. So this becomes a powerful tool. I've used it in a second paper, which should be appearing on the archives rather soon, where I model the disk in several ways to determine the distribution and fraction of stars that are initially trapped in horseshoe orbits. In other words, what is the distribution of stars that has the potential to migrate radially? So that's one application. And in the future, one thing that I would like to use, and I think that there is great power in the capture criterion in this way, I would like to use it to identify stars in in-body simulations that are in horseshoe orbits. And there's a lot that you can do with that. Something I would like to do is to draw a correlation between the amplitude of the spiral, the perturbing spiral, and the motions of stars in their horseshoe orbits. But more on that later. But for now, I hope that this introduction has been informative, and I hope that you have a moment to have a look at the paper, and please feel free to contact me with any questions that you may have.